And I forgot to turn on the recording. I'm recording now. So the square root of 9 is equal to 3 because 3 squared is 9, and 3 is a non-negative number. Now, why are we saying non-negative here? Well, because actually, technically speaking, numbers have 2 square roots. There are 2 numbers that when squared give 9. You can square 3 and get 9, but you can also square negative 3 and get 9. And so there's 2 numbers to choose from. So when we write this symbol, we're talking about what we call the principal square root, and that's the non-negative one. So even though there are 2 numbers that when squared give 9, 3 and negative 3, we only choose the non-negative answer as the square root. So if I do something like the square root of 64, we just have to think about what number when squared gives 64. Well, 8 squared is 64. And the square root of that is therefore 8. And if I do the square root of 81, well, I just have to think about what number when squared gives me 81. Well, 81 is 9 squared. So therefore, the square root is 9. And if I do 0, I just have to think about what number that I square to get 0. Well, 0 is 0 squared. So this is 0. And that's why we say non-negative instead of positive. Because if I said positive, then this wouldn't be allowed, because 0 is not a positive number, but it is a non-negative number. It's not negative, so it's non-negative. That's why we say non-negative instead of positive here, to allow 0 to be a square root. And we can do some other things. We can throw in some negative signs. So if you do negative root 100, well, here what I'm doing is I'm taking the square root of 100 and then taking the negative of it. The first thing that the number 100 sees here is the square root. So that's the first thing I do. So 100 is 10 squared, and the square root of 10 squared is 10. Right? So this is negative 10. Contrast that to what happens if I put the negative on the inside. Now I'm thinking about what number, when I square it, gives me negative 100. Well, there is no number, right? You can't square a number and get a negative number. Try as you might, you'll never be able to do it. So what we write here is we write is not a real number. On my open math, when you write your answer, you might just write DNE for this. Right? That would be the answer that my open math would accept. Or yes, I see somebody wrote 10I. Yeah, so there is a way to define this using imaginary numbers or complex numbers. But we're not doing that. So for us, this is not a real number or does not exist are our answers here. So even though there is mathematics that can take care of this, we're not doing that. But notice the difference here. Here, this is okay. We can compute the square root because the negative is outside the radical, and it ends up being part of the answer. Here, I can't take the square root because the negative is inside the radical. So this is the general strategy for doing radicals. You find a number that when squared gives you the thing that's on the inside, and that's your answer, right? The non-negative one. So we can do the same thing with cubed roots. So let me get another sheet here. So what about the cubed root of something, like the cubed root of 27? Well, the cubed root of 27 is, this is going to be the number that when cubed gives me 27. The non-negative, well, actually, I'm not going to say non-negative here. It's the number that when cubed gives me 27. Well, 3 cubed is 27. And so the answer is 3. Notice that this symbol and that symbol pretty much just cancel off. The cubed root of, let's do 64. Well, 64 is 4 cubed. 4 times 4 times 4. And so the cubed root of 64 is just 4. What about the cubed root of negative 8? Well, here's where we get a little bit different than the square roots, because there is a number that when cubed gives me negative 8. It's not like square roots where there isn't. There actually is one. Negative 8 is negative 2 cubed. Right? And so the answer is negative 2. So here we are allowed to have a negative underneath the radical, because negative 2 cubed is negative 2 times negative 2, which is positive 4. And then multiplied by negative 2 again, we get negative 8. So it does work. And so the general rule here is that when this number here is odd, we can take those roots. When this number is even, we can't. Right? So when the index is odd, you can compute roots of negative numbers, but not if it's even, like in the case of square root, right? All right, so, and for that reason, you can also do the negative cube root of 8, which ends up being the same thing, because it's the negative cube root of 2 cubed, which is the cube root of 2 cubed is 2. That's also negative 2. So those actually give you the same answer in this case. So you can contrast to what happened with the square root. And we can define fourth roots as well and fifth roots. For instance, the fifth root of 32, you have to think about what number, when you raise it to the fifth power, you multiply it by itself 5 times, gives you 32. That takes a little bit of thought. Fifth roots are hard. They can take some time to figure out. But if you go through a few numbers, you figure out that this is 32 is actually 2 to the fifth. 2 times 2 times 2 times 2 times 2. And so the fifth root of 32 is 2. And if I asked for the fourth root of 16, actually let's make it negative 16, what would you write? You'd write does not exist or is not a real number. Because we are taking an even root of a negative number, and that doesn't work. That doesn't give a real number answer. So, so these are roots. Let's see some other things we can do here. Okay, what about when we have variables? Variables are next. So if I took the cubed root of x cubed, what do I get? Well, here I'm looking for a number that when cubed gives me this, x cubed. Well, that's x, right? The cubed root of x cubed is x. And remember, like I said before, these things, it's as if they just cancel off. So if I did the fifth root of a to the fifth, I would get a. Or if I do the seventh root of z to the 7, I would get z. What if those numbers aren't exactly the same? What if I do the square root of b to the 6th? That's a 6 up there. Well, we can still do this because, remember, when I don't write a number here, it's implied that it's a 2. So we just have to think about what, when I square it, gives me b to the 6. Well, b cubed. If I square b cubed, oops, if I square b cubed, that's a 2 over here. If I square b cubed, I multiply the exponents, and I get 6. So b cubed squared is b to the 6. So I'm taking the square root of this. Well, that means that the answer is just b cubed. So notice what happened here. You can either pull it apart like this, where you write, you think about, okay, what do I have to multiply by 2 to get 6? And that's the number that goes here. And then the square root and that cancel off. Or you may realize that what we ended up doing is just dividing 6 by 2, and that's the new exponent. So that might be even a quicker way to do it. What if I do the cubed root of b to the 6? Well, now I have to think about what number when cubed gives me b to the 6, or what, not, it won't be a number, it's got a variable in it. What quantity when cubed gives me b to the 6? Well, that's b squared, right? B squared cubed is b to the 6, because to compute this, I would multiply these, and I would get 6. So this is the cubed root of this. So remember, the cubed root is the quantity that when cubed gives me this. Well, that's b squared. And again, to get from here to here, we just divided the 6 by the 3. But I'd like you to think about it this way, or this way, because in the next section, we're going to have to do it this way. Just dividing isn't always going to work. In particular, if this number is not divisible by this number, we're going to be in trouble. All right, so you're going to kind of want to get used to doing things like this. So this is a good way to think about things. Break it down so that the exponent matches the index of the root, and then you can sort it out that way. All right, let's see here. Looking through my notes. What if we have a mix of numbers and, oh, we have a question. What happened to the 2 when you squared it? Are you talking about this line here? Okay, so here, when I take the square root of something squared, they cancel off. So just like if I did the square root of a squared, that's just a. Right? So whenever I see a square root in a square, they undo each other, because what this is it's the quantity that when squared gives me this. So what squared gives me a squared? Well, a squared gives me a squared. So that's why that's got to be the answer, and that's why these things just cancel each other out. So once I find the 2 here, I cancel it with this. I hope that answered your question. Okay, so what happens if we mix some numbers and variables? Well, what if I do the cubed root of 216a to the, I'm going to change the example because it's too similar to what we already did. 15, about that. 216a to the 15. So here's the property that we need. We need this property. If I take the nth root, it could be any index, a times b, we need to know that we can do this. Take the nth root of a and then multiply it by the nth root of b. And this is the fact that we're going to use. I'm sure it's in your book somewhere. I just couldn't find it in that section. This is a kind of a product property for roots. Okay, so that's what we're going to do here. We're going to break this apart into 2 pieces. We can treat this as the cubed root of 216 and multiply it by the cubed root of a to the 15. So we can do them separately. That's what this is allowing us to do. What's the cubed root of 216? Well, that's something you got to think about a little bit. It's not immediately obvious, but when you start hunting around and thinking about it, you'll come up with the number 6. 216 is exactly 6 cubed, right? So this is the cubed root. Let me go down here. This is exactly 6 cubed. And what will I do with this guy over here? Well, what cubed gives me a to the 15? Well, a to the 5. Because if I multiply the 5 times the 3, oops. If I multiply the 5 times the 3, I get 15. And we know how that property of exponents works, right? So that's the number, that's the quantity that when cubed gives me a to the 15. So the cubed root is just a to the 5th. In other words, these things cancel out, and these things cancel out. So what I get is 6a to the 5. So when you have a product of things, you can just break it apart like this and just do them individually. And you might see more than one number or variable in there. And I'm running out of paper, so if you just, oh wait, I can see some. I was gonna go to the other room, but some over here. Okay, let's do one more. I got, let's see, the cube root of 27, p to the 45, q to the, let's make it 21. Okay, so what we're going to do is we're going to break this up into pieces. We're going to do the cube root of 27 times the cube root of p to the 45 times the cube root of q to the 21. So what's the cube root of 27? Oh, wait, we have questions. How did you get the 6 again? Yeah, so I think that might answer your question. Aviraj chatted back. 6 times 6 times 6 equals 216. Not obvious. I'm not saying that was obvious. That 6 times 6 times 6 is 216. But if you hunt around on a calculator and punch around a little bit, you'll discover that. Okay, so back to this problem. What's the cube root of 27? Well, another one. Not immediately obvious. It's maybe a little bit easier than that other one, 216. Well, 3 times 3 times 3 is 27. Right, so 27 is 3 cubed. Actually, we don't. This actually is familiar. I think we did this one already. And what is p45 cubed? Right? What do I have to cube to get p to the 45? Well, p to the 15. And what do I have to cube to get q to the 21? Q to the 7. So there's my answers. This and this cancel, that's a 3. This and this cancel, that's p to the 15. And this cancel, that's q to the 7. Right? So we've simplified it. You're basically just dividing the exponents by 3. That's all you're doing here.